So there's no Java in this presentation at all. So if you're hoping for a Java talk, you're kind of in the wrong place. Which is probably good, because I'm a rubbish Java programmer. Okay, so this is me. My name is Matt Jarvis. I am Director of Community for a company called D2IQ. D2IQ used to be a company called Mesosphere. You may have heard of us for our previous name, but we build cluster orchestration software. So we've been building cluster orchestration software using a piece of software called Apache Mesos for a very long time, and now also around Kubernetes. And I've been involved with open source software for longer than I care to remember, as you can see from the gray hair. And I've kind of worked in operations, in product development, and in this new kind of world of DevOps and automation. So this is kind of what we're going to talk about a bit today. I'm not a big fan of agendas, so we'll just skip over that slide. So how many people in the room know what Kubernetes is? Ah, cool. That's good. How many of you are using Kubernetes? Cool. Okay, even better. Right, okay, so some of you, the stuff I'm going to talk about at the start, you know, folks may be familiar with, but I find it's always useful to kind of set the tone and set the scene for what we're kind of talking about in this field of operators. So Kubernetes and all other orchestration systems that have this idea of declarative state work very well for stateless applications. And a stateless app is a program that doesn't save client data generated in one session for use in the next session with that client. So every session's carried out as if it was the first time, and responses aren't dependent upon data from a previous session. So in practice, that means that we can stop and start our stateless application, and it will basically just start executing. You know, they're kind of ephemeral. The management of them is pretty binary. And so in general, we'd run this kind of application behind a load balancer. And we can scale it up, scale it down, just by adding or removing instances. And we can also deploy new versions pretty easily, just by replacing all of the running instances. And we can have various ordering strategies for performing that. You know, we might have blue-green deployments where we're mixing different versions for testing. But fundamentally, the management of this kind of app is binary. We're either running or we're not. And stateless apps are pretty intrinsically intertwined with the move towards microservices architectures, where we connect together many very simple applications which each have a particular well-bounded function. And I guess to the adoption of container technologies to manage them, because they're fundamentally well-suited to the patterns that systems like Kubernetes give us. We just declare that we want a specific number of them, and Kubernetes will basically create them for us. And again, it's basically a binary idea. They're either running or they're not, and we don't have to worry about any complex operations to configure them before we start deploying. So if all applications were stateless, then the world of application deployment would be super simple. And sometimes in our industry, if you read the tech press, you get the idea that that's the case in the era of microservices. But unfortunately, that's not actually true. The second class of applications is stateful, where the app is retaining data or state across its entire life cycle. And whilst older, more monolithic applications like SQL databases fit into this paradigm, there are also many architectures where the individual elements making up a particular service are actually clustered together in some way. They might be sharing state data between them, or they need to be synchronized together in some way. And you know, this is a lot more complicated and is a whole area of computer science unto itself. But typically, these kind of applications have a set of lifecycle states, things we want to do to them throughout the time that they're running, which require logical ordering of actions in order to maintain operation. So in general, we can't just start and stop instances of one of these kind of applications and expect our overall service to continue to operate or continue to be performant. We might need to wait for data to rebalance, for example, or there might be multiple steps involved in an upgrade operation. And that applies not just to upgrading, but also to scaling, how we scale them up, how we scale them down, and failure scenarios. What do we do when things go wrong with them? And these operational strategies require what we call domain-specific knowledge to manage them. So they tend to be unique to that particular application. So if you're managing a Kafka cluster, the set of things that you need to do to a Kafka cluster in order to operate it are very different from the set of things that you need to do for a Cassandra cluster or for an HDFS deployment, for example. And when we look at the differences in architectures between these stateful applications, you can see that it's fairly obvious that we need to manage them in a different way. With this Cassandra, we have this kind of ring configuration, and then we look at that versus something like a Kafka deployment, and they look very different architecturally. And Kubernetes was originally entirely focused on stateless application architecture. So one of the fundamental features of Kubernetes is that the scheduler can move pods around between agents. So if an agent gets full or an agent fails, then Kubernetes will just move those pods around. And that works fine for stateless applications. They're generally running behind a load balancer. If we lose one, we just spin up another one somewhere else, and our application continues to run. But that doesn't work so well for stateful apps, which tend to like their storage and their networking not to change during operation, unless we handle that in a very specific operational way, as we talked about a second ago. So in order to try to handle the complexities of stateful applications, Kubernetes added this idea of stateful sets. And that adds some of these concepts of stable network and storage. But it doesn't actually solve all of our problems, because Kubernetes still doesn't know what's going on inside those pods within a stateful set. It's by nature a fairly generic, fairly coarse approach. And we can, as an example, we can consider something like doing rolling upgrades of nodes in our Kubernetes cluster. If we have a fictional master-slave database here running in a stateful set, and then the node running the master upgrades, we reboot it. So we might lose some transactions there in our fictional database. And at this point, the database cluster might trigger a re-election. If that's what happens, it elects a new master. And when the first master pod is rescheduled, it comes back up in a cluster with a new master. So it might be unaware of that. And that may cause issues in itself. But even if it then settles back down into its new role as a kind of slave, we now have all our nodes back up and running again. And so we roll out an upgrade to another node, potentially hitting our new master, and so on. So how happy is our fictional database cluster likely to be during those operations? And the answer is not very. And the point here is that the domain knowledge of how to safely upgrade our fictional database cluster isn't captured in this concept of stateful sets. So how do we automate and package that knowledge up of how to do those things? So no Kubernetes slide deck would ever be complete without a quote from Kelsey Hightower, and this is only from last year. And Kelsey Hightower's view at that point was you shouldn't do stateful applications on Kubernetes at all. I think things have moved on slightly from this, but it proves the point that stateful applications in this world of Kubernetes are a big problem space, even for people who are experts in the field. Somebody's added this slide into my slide deck. I'm not entirely sure what the purpose of that slide is. Let's just click through to the next one. So the emerging solution to this problem is the operator pattern. And operators basically encapsulate operational tasks in code, which can either be run when an API is invoked, they can be run automatically, be run on a schedule, whatever you need to do. So we can orchestrate application lifecycle actions using Kubernetes APIs. So operators encode this domain-specific knowledge about the particular application. How do I scale it? How do I upgrade it? How do I deal with failure scenarios and so on? And they achieve all of that using native Kubernetes APIs. And another way you can think of these operators is that they're application-specific controllers. So in the same way that Kubernetes will reconcile state, Kubernetes has a controller inside it that will reconcile state between the state that you asked for as a cluster operator to what the state of the cluster is. An operator is an application-specific controller for reconciling that state. So what are operators? And this can get slightly confusing because of how we might use this terminology. When we're talking about operators here, obviously we're talking about these controllers, but then we also have this human set of operators who are running these things. So if you get confused, feel free to ask me. But in this context, when we install an operator, what we will likely get is the operator itself. So that's going to be a controller, some controller code, usually running in a pod of its own, that manages the life cycle of the particular thing that we want to control, and where that domain-specific knowledge is encapsulated. And we'll also typically get a bunch of custom resource definitions, CRDs, and CRDs extend the Kubernetes API to address new resource types. So they add a new type, you can put some data into it and instantiate it. In this slightly fictional example here, we've got a CRD for a MySQL cluster that, you know, in this example would give us a clustered MySQL instance. But it's important to note that typically these things are unique. So an operator for Elastic will be a different operator from an operator for Kafka. They're purpose-built for each application. And up until now, there have been two main ways, although there are a few other different ways these days to do this, but there have been two main ways of building operators. The first one's the operator framework. This originated inside CoreOS, and who were CoreOS engineers originally kind of coined the idea of operators. And CoreOS was acquired by Red Hat, so this is mainly developed these days by Red Hat and IBM. And whilst you can build operators using Ansible or using Helm charts, there's also a Go SDK. And Ansible and Helm-based operators will tend to have limited functionality, and most operators built using the operator framework are built using the Go SDK if you want to do anything complicated. And then there's the KubeBuilder project. That's part of the API machinery special interest group in Kubernetes. And it's focused on extending the Kubernetes API. And again, you need to write a lot of Go to build during this, using this. So building operators can be really complex, and it requires a lot of knowledge about how Kubernetes works internally. As well as that, it requires a lot of Go expertise. You know, these libraries are complex things, and that's all as well as the domain-specific knowledge you need about the actual application you want to build a controller for. So, you know, obviously, relatively simple tasks can be automated pretty easily, but if you want to get into having full coverage for a particular application, then these things can get very big very quickly. So adding a replica to a database might be a pretty straightforward action, might only need one command. But if you want to fix a corrupt write-ahead log file, that might take a whole set of different tasks that you need to run in order to get that to be fixed. So the engineering effort that goes into high-quality operators is really considerable. As an example, one of the major NoSQL vendors has an operator. It's probably one of the most feature-rich ones that are out there these days. But it's over 50,000 lines of code, and it took over 1 man-year to write. And even something like the etcd operator is over 9,000 lines of code, and etcd is a fairly simple application in terms of how you manage it. So I think the point here is that that's a huge amount of investment for any engineering organization to make just to build something to automate some things in Kubernetes. Unless you're a software vendor, putting that much effort, a man-year of effort and that many lines of code to maintain is a kind of unreasonable ask for you just to be able to manage your stateful app in Kubernetes. And here's another example. This is, I think this is an Elastic one. This again is over 60,000, over 50,000 lines of code. And so the other emerging problem in this space is, as we said a couple of slides ago, that there's all these things are unique to those applications. So if you've got a big Kubernetes cluster and you're running lots and lots of stateful applications, you're going to have lots and lots of these purpose-built controllers running in your cluster. And so the management overhead of running all these different things, some of them built using different toolkits, is going to increase fairly dramatically. And people are already starting to talk about needing to have operators to operate operators, all getting very meta. So when we started to look at the operator landscape a couple of years ago, it seemed like it was a pretty familiar problem space. In the Mesos world, most applications running on top of Apache Mesos are stateful apps and always have been. That was one of the things that it was written for originally. And so Mesos has this concept of frameworks which actually end up looking a lot like an operator. They control all these different life cycles for these stateful apps. And in the Mesos world, we'd seen developers having to implement all the same steps, a lot of complexity being expressed in number of lines of code and time to implement. And so we had created an SDK for Mesos to make it simpler for people to write Mesos frameworks. And when we looked at the Kubernetes landscape, it just looked like a very similar problem space. So we created the KUDO project to express those same ideas from the Mesos SDK, but in Kubernetes. And KUDO is an acronym. It stands for the Kubernetes Universal Declarative Operator. And rather than implementing a custom operator for each individual application, KUDO provides this universal operator with a set of concepts built into it that cover a lot of use cases for managing these kind of applications. So you have this idea of basically runbooks, and I'll talk through some of those concepts over the next few slides. But it basically allows you to ship your application and a set of operational runbooks together in a single thing. And it allows operator developers to define almost all of that code declaratively in YAML. So without writing any Go, without really needing to know what's going on inside the Kubernetes scheduler, you can create pretty complex operators just using YAML. So it provides a framework for operational sequencing and actioning. It's a fully open source project, licensed as Apache 2.0. And we've been actively developing it and building community around it for the last 12 to 18 months. So in comparison to those other ways of building operators, Kudo is polymorphic. So we don't build a separate operator for every application. Kudo can basically become an operator for that application given the right configuration. And you don't need to have very deep knowledge of Kubernetes or really write any code. Just by defining lifecycle phases and actions within YAML, we can orchestrate applications using the built-in custom resource definitions which Kudo provides. And Kudo's ultimately just Kubernetes. There's no separate DSL you need to learn. There's no external data stores, no proprietary APIs. It's just using standard Kubernetes stuff. So as a result, we think it's easier to learn. It supports all the native Kubernetes tooling, so things like Kustomize, like kubectl, and it maps basically to exactly the same resource model as other Kubernetes resources. So there's some core concepts that we need to understand when we talk about what Kudo is. Firstly, in the world of Kudo, this concept of operator is the description of a deployable service. So this is a CRD, and we'll see that when it comes to the demo. And then we have this idea of operator version. An operator version it represents the particular implementation of an operator. It contains all those runbooks, all the objects, all the parameters for that operator, but for a specific version of that deployable application. So the purpose of it really is to provide Kudo with all the details it needs to become an operator for a specific capability, so say Kafka, but also for a version of Kafka. And the reason why that operator version it exists really is so that you can run multiple versions of a single application within your cluster. So it includes all the configuration, all the lifecycle hooks for deployments, upgrade, rollbacks, whatever you've configured within that particular operator. It's like a complete definition of the application that you want to be installed, with a bunch of parameters that you can override. And then the instance is the CRD that it ties a particular instantiation of an application, so the particular thing, so a Kafka cluster, for example, to an operator version. So it's an actual deployment of the thing that we want to control using Kudo. And when you create an instance, you can override parameters or whatever that are set as defaults in your operator version. And then we can have multiple versions of the same operator running at the same time. So this covers the use case, for example, where you might have an application that's tied to a particular version of Zookeeper or something like that. So you need to be able to run multiple versions of that particular app within your cluster. So plans are how Kudo operators convey progress through service management operations. So it's this hierarchical kind of structure. So plans composed of phases, which are composed of steps, and then steps contain one or more tasks. And all this stuff is defined in YAML, which we'll see again when we come to the demo at the end. Phases and steps can be configured with a execution strategy. So they can either be serial, where a step needs to be completed before we move on to the next one, or they can be parallel, where we just say you can run all these at the same time and it's safe to do that. KUDO also includes a CLI extension to kubectl, so we can do things like install KUDO packages, install KUDO operators natively from inside kubectl, so we don't need to switch out and use a separate CLI. And again, we'll see some of those when we come to the demo in a second. And then from a kind of high-level architectural perspective, this is what KUDO looks like. So within our Kubernetes cluster, we've got a controller pod, which is running our KUDO controller. We've got a bunch of CRDs. And then the kubectl CLI command allows us to install operators either from GitHub, from the upstream KUDO repository, or we can install operators directly from a local file system. And then in our cluster there, we've got example of the Kafka operator running with 2 different versions of Kafka and an instance of Kafka 0.2.0. Okay, let's see whether this all works. Okay, so this is a clean Kubernetes cluster that I deployed into AWS earlier. I hope it's still running. Yep. So we can see there's nothing running in it at the minute. I'm just going to use my handy cheat sheet here. So we do have a bunch of CRDs installed here. We have some. This is actually deployed using our installer Convoy, which installs a bunch of useful things like Prometheus monitoring and stuff by default. But if we let's grep for KUDO. We can see we haven't got any KUDO CRDs there. I'm just running kubectl here, by the way. The K is just a alias to kubectl. And if we say K get operators, so what's been returned from our Kubernetes cluster there is basically I have no idea what an operator is. You know, that's why we get that error. It has no idea what operators are. So now what we want to do is install KUDO into this cluster. So with the kubectl KUDO CLI extension, we can just do KUDO init, and that's going to install KUDO from the upstream GitHub repository. So it's installed a bunch of CRDs and installed the KUDO controller. So now if we look at get CRDs, we can see we've got these 3 custom resource definitions: instances, operators, and operator versions, which we talked about a couple of slides ago about what those are for. And if we also look at API resources, again, we've got a bunch of API resources there for the same things that are namespaced into this kudo.dev API group. And then lastly, we can actually see that we have our controller pod for KUDO running there, which is basically the controller manager for the whole of the KUDO operator stuff. So, first thing we're going to do is I'm going to install a Zookeeper cluster. So I know that the upstream version of this Zookeeper operator for KUDO will give me a 3-node Zookeeper cluster by default. And we should see straight away that we've got our cluster starting to deploy there. And again, I can use the KUDO CLI command there to show for package list what plans are available for my Zookeeper operator. And we can see we've got a deploy plan and we've got a validation plan. And then those break down into these steps. And for our Zookeeper deploy plan, we can see that says that we can execute in parallel. So we don't actually need our first Zookeeper instance to come up before the other ones come up. We can bring all those up at the same time and they'll synchronize between themselves. And we can dig a bit deeper into that particular plan, again using the Kudo CLI extension. We can ask the status of that particular instance, and we can see our deploy plan is in progress, and this Zookeeper phase in parallel is complete, and we're just now it's running the validation phase to make sure that that Zookeeper cluster is running. And we can also describe that particular instance, so we can see a nice set of metadata there about what that instance is, what version it is, what the timestamps were, all that kind of stuff. And within this Zookeeper operator, KUDO operator, I know it's going to create a stateful set, which we can see there. And if we now do kget operators, we can see not only does our cluster know what an operator is, but it's got this, this Zookeeper operator installed in it. And we can see that it's got an operator version, which is the Zookeeper 0.3.0. And if we go and look, I've just got a checkout of the operators repository here, which we'll just go and have a quick look at. And I'll show you what these look like in practice. So that's just a checkout of the upstream KUDO GitHub operators repository, and these all have this totally standard layout with these three folders at the bottom level. And again, these are completely standard. We'll always have this operator YAML, params.yaml, and a set of templates. And the operator.yaml is a set of tasks, so we can see up here, and a set of resources that are attached to that task. So when we run that infra task, it's an apply task, and it's going to apply all of these YAML files. And that's the same for all the way down about which YAML files are involved. And then here we define what the plans are. So we can see the steps, the phases, and then the steps. And for that step, the deploy step, those two tasks are going to be run. And further up here, we obviously see which YAML files are going to be run when that particular task gets invoked. And if we look at our params.yaml, this is where all the overridable parameters are defined for this particular operator, for this Zookeeper KUDO operator, what the defaults are, and all of these in capitals are overridable when we instantiate a particular Zookeeper operator. And then if we go into our templates folder, these are the YAML files that are referred to in the top level operator.yaml. And what we'll see in these files is templating, so that we see where we can override particular parameters within that YAML. And KUDO handles all of those templating when those CRDs are loaded into KUDO. So let's just go back here. What are we doing? Right. So, and the last thing I just want to show you was when we describe the operator version contains all of that templated YAML. So when we install that particular operator, what happens there is all of those YAML files for whatever tasks need to run all basically get sucked in from that repository and get created as the operator version. So we can see these are all the different template files that were in that folder that I just showed you, with the overridable parameters, so that now KUDO knows internally which things it needs to run when it wants to do a particular task. Right, so next thing. So now we've got a Zookeeper cluster, I'm going to install Kafka. And Kafka has a dependency on Zookeeper, which is why we installed Zookeeper first. Kudo does actually understand dependencies internally, but I wanted to just show how that was happening by doing that manually. So the first thing I'm going to do is I'm going to install the Kafka operator, but I'm not going to actually instantiate a Kafka cluster yet. I'm just going to install the operator into the cluster. And this is, when I do it like that with no arguments, that's just using the one that's in the upstream repository. And you can see this one's fairly simple. When I list the plans for it, it's only got a couple of different plans, and they're not particularly split out. So I've got a newer version of this operator, which is in my local checkout. So I'm just going to go back to my operator checkout, Kafka. Just make sure my Zookeeper cluster is all complete. Yeah. So now I'm inside the checkout of that particular Kafka operator. So now I can use the Kudo CLI to actually look at the operator locally. So I ran the command there where I list plans dot, which is going to give me current running folder. So you can see in comparison to the one I've installed in the cluster, this one's much more feature rich. So the tasks are broken out, and it has a whole set of additional plans that are available to this operator. And I can also list the tasks for this particular operator. So again, those were, when we looked at the top level operator.yaml file, this is where this stuff is defined, but we can see using the CLI command that this operator knows about all these different kinds of tasks. And we've got applied tasks here, which basically just do the equivalent of doing kubectl -f apply with a set of YAML files. But we've also got this new type of task here called pipe. And what pipe tasks do is allow you to take the output of one task and use it as the input of another task. So in a lot like a Unix pipe. In the case of this Kafka operator, what this is going to do is generate a shared certificate for the whole cluster. So, and then that certificate can be shared when we bring up new pods within that cluster. And we can also look at the parameters that are available to us in this particular operator. So we can see we've got tons of overridable things that we can do with this Kafka operator that we're looking at on the local file system. So let's go ahead and install this one. And what I'm going to do here is install this newer version of the Kafka one, but I'm going to override, using this -p file, I'm just going to override one of the parameters that we defined earlier. So by default in this operator, I think it's 2048 memory per Kafka node, per Kafka broker. And so we're going to just, for the minute, install that with 1024 meg of memory. And we should start to see. So we can see that pipe task ran right at the start. That's now starting to finish. And we're bringing up the first instance of our Kafka cluster. So for people who've deployed Kafka, we know that we need to bring up each node in a serial fashion. So we need to wait for one to have completed before we start bringing up another one. And we can see that, again, using the Kudo CLI command. We can see that for the Kafka deploy phase, we need to run things in serial. So we're going to have executed this task first, which is generating our certs. It's done some other smaller tasks about configuration, and now we're actually deploying the app. And again, we can describe the instance exactly the same as we saw with our Zookeeper operator, and we can see our execution of the deploy plan has started. So now we've got a couple of our brokers running, and we're just waiting for our final broker to come up there. Yeah, so it's all showing as in progress there. So let's just watch that for a second. Right, okay, it's actually finished. Right. So with two, I've run a lot of other commands there to poke around in with what was actually happening, but effectively with two commands we've built a highly available Zookeeper and Kafka cluster running in our Kubernetes cluster, and you know, we can prove that actually is a working Kafka cluster. So we can use kubectl to look at the logs of one of these instances. It doesn't matter which one we look at, and we're going to look for a Kafka version in the log. So it looks like from the logs that Kafka is running correctly. And then what we can do is just start a shell within our Kubernetes cluster. This is just going to run a busybox image and just give me a shell, which is now, that shell is inside my Kubernetes cluster. And I'm just going to connect there to the service address of that Kafka cluster and get the metrics API. So we can see that's a fully working Kafka cluster there. It's putting out metrics to its metrics API. So now we're going to kill that. And I'll just show you one other thing here. So included with this particular operator, I know, is a bunch of resources. So I've got a definition here for a Grafana dashboard. Big copy. So if I now go back to here, I want the other window. Just bear with me 1 second. Let's just get out of that. So this is the dashboard for Convoy, which is the deployment tool that I use to deploy the Kubernetes. And it comes pre-configured with a whole bunch of useful stuff in it. This one's got Kibana, Prometheus, Grafana for logging and monitoring. And so I'm just going to open that Grafana dashboard. And I'm just going to do import. And I'm just going to paste that JSON from my operator from that Kafka operator into Grafana. I'm just going to build a dashboard for it. So there's a dashboard now here, but there's no data going into there because we haven't actually linked up Kafka to Prometheus. So what we need to do now is one of the parameters that this KUDO operator gives us is this service monitor parameter. So what we've done there is just to change that add service monitor boolean to true for our instance of Kafka. And now that service monitor endpoint should get picked up by Prometheus, and we should start getting monitoring data into our dashboard. This may take a couple of a minute or so for us to get any data into there. So let's just talk amongst yourselves. Come on. Hang on. This always decides to be super slow when you're actually trying to do a demo of it. Right, okay. So now we can see our dashboard's starting to fill up with data that's coming off our Kafka cluster that's running there in Kubernetes. So the next thing we want to do is just to, and we can see what that particular task did when we do kubectl get service monitors. So a service monitor is a type that's provided by Prometheus. So that particular task that was generated when we said add service monitor equals true has added that service monitor for us automatically. So the next thing we want to do is to just update this Kafka cluster. Excuse me. So what we're going to do this is update 2 parameters. We're going to change our broker count to 5, and we're going to push our broker memory back up to 2048 meg rather than 1024. And so our Kafka instance now is starting to update. So again, we can see that that we've got a certificate generation happening there because we're going to start adding instances to our Kafka cluster. So we can see we've got our 4th instance creating there. So our 4th one's now up and running, and we should start seeing our 5th instance adding to that Kafka cluster. Here it comes, so it's in pending at the minute. It'll start creating the container in a second. And then once this is all running with 5 instances, KUDO will then start doing changing the vertical scaling of the instance by applying the broker count change. So within that KUDO code, it knows it's not going to try and do everything at once. It needs to extend the horizontal scale first, and then start, as you can see, these are starting to terminate. And they're going to terminate in order, keeping that Kafka cluster up all the time, and then it's bringing them back with that expanded broker memory. And I think probably if we look now in our Grafana dashboard, we can see we've got those 5 brokers defined. I don't think we need to watch that. Okay, and let's just delete that shell. So it's just resizing the last one there. And restarting it with the upgraded broker memory setting. And once again, we can prove that is a working Kafka cluster with 5 nodes. If we start another shell, and we look again at that metrics API directly from the Kubernetes cluster, and we can see that we've got metrics coming out of that, so we know that that Kafka cluster is fully working. Okay. Yep, so there we've got our 5-node Kafka cluster and 3-node Zookeeper cluster. So let's go back to our slides. Let's just do that. I was lucky that worked. Okay, so there's a bunch of stuff on the Kudo roadmap. It's pretty early days. Like I said, it's a small team of people developing this, and it's still under very active development. I normally have to try this demo every time I go and do this talk because something's changed or that I need to take into account. But there's a bunch of stuff that is coming up on the roadmap that's going to make Kudo even more useful. The first one is this idea of dynamic CRDs. So when we looked at the structure of those operators on disk, and you could see how those tasks and steps and phases were defined in YAML files. So what dynamic CRDs will allow you to do is update a running operator with new plans. So without having that stuff on disk, a human operator can say, well, I've got a new way that I want to do backups, for example. And you can inject that into a running operator while that operator's in your cluster. We've got a bunch of work going on being able to extend Kudo from other sources, so being able to use things like Helm as a starting point for a Kudo operator. In common with lots of projects in the Kubernetes ecosystem, there are various other languages that are being looked at as a replacement or an alternative to using YAML. One of the challenges for defining things like this in YAML is you end up with these very long YAML files. And to anyone who's operating Kubernetes, I'm sure you know the pain of managing those. They're not very human readable. So there's a variety of things like Starlark, like Q, pretty early projects, but starting to look at ways of reducing that reliance on pure YAML files. And pipe tasks, we actually saw an example of pipe tasks there where we can use where we can pipe the output of one task into the input of another. We saw that certificate generation in that upstream Kafka plugin, Kafka operator. And a bunch of stuff around making it easier to develop these things. So skeleton generators, so you don't have to write all the code yourself, linters, all that stuff. The roadmap is all available in GitHub. And if any of this has been interesting, there's a bunch of different ways that you can find out more. Kudo is all on the website at kudo.dev. Our GitHub organization Kudo Builder contains the Kudo itself, plus all the operator repository, and actually the kudo.dev website. There's the #Kudo channel on the Kubernetes Slack, which is where all of the development work happens. We also have a mailing list with the URL there. And there is a bi-weekly community meeting video chat. You're welcome to come along, hang out there, ask questions. As I said, we're actively trying to build community around this at the minute. And so everybody's welcome to kick the tires. If you want to develop operators or you want to work on Kudo, we'd love to have more folks working on this. That's all I've got, so I'm happy to take any questions.
Great presentation, thank you.
Thank you.
So my question is, do you think it could replace Helm charts for stateful applications?
Yeah, well, so I mean, I think there's a place for lots of different things, right? I mean, I've heard people in the operator community, in the wider operator community, say, "Oh, operators will make Helm charts obsolete." I don't think that's necessarily true. I think it's just having different things in your toolbox. One of the interesting things when I have given this talk is that we've had lots of people ask about, this came out of wanting to orchestrate individual clustered applications, right? That's where the operator thing, the pattern comes from, like, manage a Kafka cluster. But then I've seen a lot of people say, well, I've got a microservices architecture. Can I like write an operator to operate all of that, to deploy it as one whole stack rather than, which is kind of what Helm does, right? But in that deployment phase. But so I think that the whole space is going in interesting directions. And I think we'll see more and more of these kind of meta operators to operate a whole stack rather than just one thing. And you know, in deployment terms, that's what Helm's really good at the minute is deploying whole stacks of things.
Because for me it looks kind of like another layer on top of Helm. It's like deploying multiple Helm upgrades one after another.
Yeah. Exactly. So you've got that controller manager there, which is reconciling state, you know, in the same way that the Kubernetes controller manager is reconciling state. And that's ultimately what all operators, no matter how you build them, do. They've got that controller manager there running all the time with a reconcile loop going, you know, do a backup, do this, upgrade my cluster, scale me, you know, whatever activity you want to do to that particular application. But rather than having to, you know, apply a Helm chart or whatever, you've got a controller manager running there to do that stuff all the time that knows exactly how to do it. I mean, I think the sweet spot really for KUDO is, like I said at the start, that lots of the other mechanisms for building operators at the minute require you to have loads of Go expertise and understand how Kubernetes works under the hood. Whereas, you know, what KUDO gives you is that simpler place to start with that concept of plans, which is effectively about runbooks, right? It's just runbook ordering, but it's that you've got that abstraction there straight away to just go, you know. I mean, if I'm an operator of Kafka, a human operator of Kafka, there are things that I do every day that I know about, right? That I could say, well, here are the 5 commands that I run when I want to, you know, do something to my Kafka cluster. And I guess that's one of the places where KUDO's really useful is, you know, because that guy probably doesn't know how to write a bunch of Go code or doesn't understand, you know, how the Kubernetes scheduler model works. But you don't need to, because it's just a way of representing that stuff in YAML. Does that answer your question? I went around the houses there a little bit.
I would like to ask a question. Where is there some general website that holds those operators or something like that?
The operators I've just shown. Yeah. So
you can install Zookeeper and magically KUDO knows what to do.
Yeah, so the operators I just showed for Zookeeper and Kafka live in the upstream KUDO repository. There's a set of sample operators that we've built to show people what it could do. But KUDO gives you the ability, like I showed hopefully towards the end, where you can also install ones you've built from your own repository, and there will eventually be a mechanism for merging different repositories together. So you can say, well, I've got my local ones here, but I also want to use these ones from the upstream KUDO repository, and the KUDO CLI command will have some mechanism to reconcile those two as a single view.
But it uses some internet connections to actually fetch that.
Yeah, well, it did in this case because I used the KUDO CLI. But if what you're asking me is how would I do it if my Kubernetes cluster didn't have an internet connection, then you would you can set that repository URL. So you would have a git checkout that's within the confines of your security policy or whatever. You know, there's lots of different ways of doing that. I think with fully air-gapped at the minute, I'm not sure whether we test completely air-gapped at the minute. There may still be an internet requirement, but it's definitely been discussed in the development team because I know we have, I mean, although the project is separate from D2IQ, you know, we also have, you know, consulting offers with KUDO, and I know we have customers who have fully air-gapped clusters. Does that answer your question? Okay.
Are there any not open source operators already implemented and used in production? Do you know if maybe some companies that you are?
Yeah. So you mean right? So yes. And if you look at the the KUDO Slack channel or the mailing list, I know that well there's in terms of ones that are out there in the open EBS operator is written with KUDO, but I know there are folks from companies like Salesforce, for example, who are using it internally, and a bunch of other folk. I mean, the next step for us as a project is that we are we submitted for CNCF sandbox status. So the idea is to donate this upstream and have it as part of the wider CNCF landscape, and we're hoping that's going to happen over the next few weeks. But like I said, interestingly, we also get a lot of people who want to orchestrate whole stacks, which wasn't where it kind of came from, So because then it becomes like almost like a dynamic configuration management thing rather than just being an operator, if you understand what I mean.
Can I somehow use KUDO and other operators that are already there and to
mix them to
make better with both tools to make that work with each other?
Yeah, so that's another interesting point that there's work going on in the KUDO community around. Is I think what you're asking is about conformance, right? So like if I've got an operator written using the operator SDK, and I've got an operator written using KUDO, and maybe one written using KubeBuilder, how can I guarantee that they work together? And at the minute, there is no guarantee for that, other than in theory, an operator should provide you with a working version of that particular application at the end of it. But you're right, that's an emerging problem space. So we actually spun out we wrote a conformance testing tool inside KUDO, and that's just being spun out into a separate project called Cuttle that I am going to start going around meetups talking about, and what we would like is to try and get Cuttle more widely used as a conformance tool, so that you could say, well, I like my Zookeeper operator I built using Operator SDK, but I want to run the Kafka operator that I built using KUDO. But I need some way of knowing, if I upgrade this one, what does it do? And you're right, at the minute, there is no conformance testing in that sense. So we've had there's actually quite a lot of collaboration starting to happen between the different development communities involved in operators generally. The folks behind the Operator SDK and the KUDO project, and there's a couple of other smaller projects as well that are, and those folks are starting to talk at KubeCons and things like that about how do we set standards, how do we, make sure that these things interoperate with each other. Well, thank you, folks.